Yeah, hi, it's exciting to be here. I'm Ranveer Chandra. I'm a PhD in computer science. I'm a computer scientist, but I'm learning a lot over the last few years since I started this project at Microsoft. The goal of this project is to enable data-driven agriculture. That is, there were so many discussions today about precision application of fertilizer, knowing what the nitrogen content is, what the carbon content is, how your plants are doing, everything to do about precision farming. So that's the kind of thing we want to enable. What we are calling this is data-driven agriculture. Some of the things you could do with data-driven agriculture, as all of you probably know, is you could build maps of farms like this, and within the farm, you could overlay it with data. For example, what's the soil moisture level, what's the soil nutrient level, what's the carbon level throughout the farm. If you could build maps like this, as you all probably know, you could enable techniques like precision agriculture. You could apply water where it is needed, pesticide where it is needed, nutrients where it is needed. And precision agriculture has been shown to improve yields, to reduce costs, and is also better for the environment. And this is what most of the speakers this morning talked about, the benefits once you can start doing precision application of any of these inputs. And in fact, once you start getting the data from the farm, it would enable a lot of new scenarios. A lot of new technologies can come for agriculture. For example, digital advisories, traceability, a lot of new scenarios which right now are just difficult. The thing is, precision agriculture was proposed back in the 80s. It's been 30 years since then, and the technology still hasn't taken off. We all talked about how it could help enable sustainable agriculture, but the cost of getting this data from the farm is really high. Just to put this in perspective, I was at UC Davis when I started this project a couple of years after that. There was an expo going on. Lots of companies were presenting their latest and greatest precision ag equipment. And the cheapest package that was available there were 5 sensors for $8,000 and a recurring cost. For most farmers, what's the ROI? If I put in a sensor, all it is telling me is what's the value here, not what's even 10 meters away. So that's what triggered the start of this project, at which point our mission was to bring down the cost of these data-driven agriculture solutions by 2 orders of magnitude. So that's what we are after. Of course, it'll take some time to get there from 8,000 to 80. But I'll talk about a few ways in which we think we can get there. So the first reason existing solutions are expensive is because of the connectivity issue. And I was just talking to Greg over lunch. He's very interested in robotics. He's building a lot of where robotics can bring a lot of benefits to agriculture. But as we were discussing, one of the key challenges is how do you get connectivity in the middle of the farm? The farmer's house often has some sort of connectivity to the cloud. They pay for broadband. They might have 1 to 3 megabits per second connection. But the actual farm is a few miles away. Even though connectivity might exist when you plant the seeds, by the time the crops grow, the connectivity is gone. So then the question is, how would you get data, not just from sensors, from drones, robots, tractors, from the middle of the farm to the farmer's house? To solve this problem, we use a technology that I personally have been working on since 2005 called the TV white spaces. What TV white spaces enables is imagine if you have a Wi-Fi router that you could access a few miles away. That would be cool, right? Right now, as soon as you exit your building, your Wi-Fi is gone. And the way we did that was we took a Wi-Fi signal and we put it in empty TV channels. This is TV you watch using these antennas, over-the-air TV. You know, on some channels you get a transmission, on the other channels, all you see is white noise. The technology we developed was a way to take a Wi-Fi signal and put it in these noisy TV channels in a way that doesn't interfere with your TV reception in an adjacent channel. So the benefit is that compared to Wi-Fi in the same power level, in UHF TV channels, your signals go 4 times farther. In VHF, they go 12 times farther. And this is in free space. Once you put in trees, crops, canopies, your signals just keep going through. So we built this technology back in 2010. The FCC chairman came to visit Microsoft campus, and this was made legal in the US in 2010. Since then, we've gone out and connected high schools, hospitals, libraries, dispensaries in various parts of the world using this technology. In fact, in 2017, Microsoft launched an initiative called the Airband Initiative, where Microsoft is putting in money to connect rural America, actually different parts of the world, to broadband. We've made a pledge to connect 3 million rural Americans using this technology. By the way, this is now legal in US, UK, Canada, various countries worldwide. And the key insight, by the way, in the context of agriculture, was that TV towers are where people are. You have TV towers in cities. You have them in DC, in New York. The farms are away from the cities. So if you turn on a TV in the middle of a farm, most of the channels will be just white noise. Even if you have 20 TV channels that are just white noise in the middle of a farm, and I was giving this talk at a corn growers conference, and a lady farmer, she raised her hand and she said, 20, most of the channels are just empty where I live. So even if 20 are available, we are talking of half a gigabit per second of available capacity in the middle of a farm. If you have that much capacity, you're not just connecting sensors, you could be connecting drones, cameras, streaming a lot of information that right now you just couldn't gather. So the future we envision is just like Wi-Fi connects your house, this technology can be used to connect your entire farm. You just put this antenna in and miles around it gets connected, streaming a lot of data that you just couldn't get from the middle of the farm. So the second key challenge, the first was connectivity. The second reason existing solutions are expensive is because it's just hard to build maps like this. The number of sensors that are needed to build maps like this are enormous. Like, for example, if the question was, what is the soil moisture level 6 inches below the soil throughout the farm? You would need a sensor, say, every 10 meters because soil moisture just varies from row to row. So the question we asked was the last bullet here. Can we build a map using very few sensors? To solve this problem, we decided to use drones. These are UAVs. You can buy them for about $1,000. They have a camera at the bottom, and they can cover large areas very quickly. And the key IP we developed was, instead of just using sensors, you could use aerial imagery to interpolate the data, where we use AI and machine learning so that wherever you have sensors and you have aerial imagery at that location, you use that to train the machine learning model, and then use that machine learning model to predict the values in other places where you don't have sensors. And later on, I'll talk about how accurate this is. The thing is, one of the reasons I started this project at Microsoft was I grew up in India. I grew up in Bihar. I know many of you have been to India. Bihar is one of the poorest states in India. Back then, when I was growing up, I spent a lot of my time in my grandparents' farm in Bihar. Back then, I hated agriculture, anything to do with farming, because these villages didn't have electricity, they didn't have toilets. That wasn't a place I was looking to go to. But I did end up going because you end up spending a lot of time with your grandparents when you're growing up. But that exposed me to a lot of problems in that space, and that's one of the personal passion as to why I'm doing this project. So while drones are great, you really can't use drones in places like Bihar or in Africa or sub-Saharan Africa because drones are expensive. They still cost $1,000. They have battery issues. Most of these drones would only last, say, 30 minutes, that way if you're lucky. And there was also another issue, which was regulatory. In some countries where we wanted to fly a drone, you needed to get permission from the Ministry of Defense, at which point it wasn't going to happen. So then the question is, if you cannot fly a drone, how can you get aerial imagery of a farm at low cost? To solve this problem, we decided to go low tech. We are using helium-filled balloons, which are about 4 to 5 feet in diameter. We built this mount, which is connected to the balloon, where a farmer can put their smartphone with the camera facing down with a battery pack attached to it. And this thing goes 150 to 200 feet and can take images of the same part of the farm for 4 to 7 days. So there is a farm close to Microsoft campus where we do a lot of demos. So Bill Gates came to that farm. He blogged about FarmBeats and Gates Notes. So this is a smallholder farmer. Every winter in Seattle, we get a lot of rain. Whenever his farm gets flooded, right now, every morning if he comes, if he sees any amount of flooding in the farm, he throws away all his crop because he's not allowed to sell any crop that is touched by the flood. With this technique, he actually has visual proof to see which parts of the farm were actually touched by the flood and throws away those crops. In fact, in places like India and Africa, where labor is inexpensive, someone could just walk around with the balloon or put it on a bicycle or a tractor. And based on that, you can then apply computer vision techniques to start stitching together these orthomosaics of the entire farm. Now, this is great for some places where you get imagery. Of course, you can't envision that every farm in the world is going to be imaged like this. You have to rely on satellite data. But satellite data, one of the big problems with many of you who have used it, is that 77% of satellite imagery have clouds in them. So the first thing we do is we just throw away any image which has clouds. So from all the way from seeding to harvest, you get, say, 12 to 13 clean images, which is not good enough. One of the new innovations we've come up with is to see through clouds using a technique we built called SpaceEye. So what we've done is we're using artificial intelligence to reconstruct what's happening below the clouds. The way we are doing that is we are relying on another satellite, which has SAR in it, synthetic aperture radar. SAR, because it is radar, goes through clouds. We use that and a new AI technique we've developed called partial observation GANs. This is generative adversarial networks to reconstruct what's happening below the clouds. I know these are ML terms, machine learning and AI terms. I'll just give you a brief primer on that. So GANs are what many of you might see these days in terms of deep fakes. A lot of you might have heard of deep fakes. So the way this works is if I have an image and I block out certain parts of the image, I can reconstruct this image on the right. Same thing with Albert Einstein's figure on the left. You can remove his wrinkles. As you can see, what's going to happen is you can create a much younger version of Albert Einstein using this GAN technology. On the right, what you're seeing there is someone photobombs your image. What you can do is you can just wipe that person out. And using this technology, which is generative adversarial networks, you can reconstruct something which is real, which looks real. The thing is, it's a fake. In fact, this technology is so advanced, you can start doing deep fakes. So this is, I'll just go back one slide. So this technology is what we call deepfake. So there are others, if you want, after this talk, I can show you more examples. You can turn a horse into a zebra. You can take a picture of, say, Susan McCooch sitting here and replace with someone else in the audience. So one of the big problems is you could be watching a video these days and you don't really know whether it's authentic or not. Well, that's a challenge. In this case, what we built was, instead of creating fakes, we used the fact that radar signals from another satellite, they reflect differently from different materials, from metal to soil to different crops. The reflections are different. And if you use that to train the model, what you can do then is start constructing satellite imagery, even though right now it would be cloudy. So on the left, what you're going to see is what we get right now. On the right is what we are able to build using this technology called SpaceEye, using AI and machine learning. What you can now do is every few days, every 2 days, reliably, you can start getting an image of what your farm looks like. And this is not just for RGB, this is for multispectral and hyperspectral imagery, and we are getting over 90% accuracy when we are constructing the satellite imagery. So now going back, the way the system works, I talked about this problem of building these heat maps. So you get sensor data, then you get data either from drones or balloons or satellites. You use that to train a machine learning model using very few sensors, and then using AI again, you interpolate to start building these maps for that farm. What we showed in the paper is using these techniques, you can build, using aerial imagery, you can build these maps which are 3 times more accurate than existing schemes that do not use aerial imagery, that just rely on sensors on building these maps. And we've done this for soil temperature, soil moisture, and soil EC, where we've created these maps and with pretty high accuracy. The third challenge I'll briefly touch upon is I talked about how using the TB white spaces, you can make sensors more inexpensive, communication more inexpensive. Using AI, you need much fewer sensors than what you would otherwise need to build very accurate maps of the farm. The third challenge is that, well, over the white spaces, you can get a lot of data to the farmer's house, but the farmer's house doesn't have great connectivity to the cloud very often. Many farmers in the US, they pay for broadband, but all they get is 1 to 3 megabits per second connection to the cloud. So the question then is, if you gather large amounts of data, but you can't send it to the cloud, how will you bring the benefits of computer vision and artificial intelligence to the farmers? Our key insight was that most farmers have PCs. If they don't have a PC, we ship them a PC like the ones you're using here, which sits in the farmer's house or office and does a lot of compute sitting in the farmer's house or office. All the computer vision and machine learning is running there, and it sends summaries to the cloud, where you then merge with other data streams, satellite data, weather data, and so on. I'm just double-clicking on that box, the PC. Everything you see in this big gray box is running in the farmer's house or office. It gets data from sensors, from drones. It does the computer vision. It does this, the orthomosaicing, the machine learning, all of that stuff. The heat maps are generated there, which then drives these AI algorithms, the one you're seeing in the rightmost column. All of this data is then lazily synchronized with the cloud, not sent right away, so that even when the farmer is not on the farm, they can still see the data from the farm. So this is the future we envision of how the data is going to be captured from the farm, flow through an edge system. It's like, imagine a small cloud sitting in the farmer's house all the way to the cloud. This end-to-end system can then be constructed. So we've deployed this system in various parts of the world, and from small farms, which are 0.5 acres, to farms which are 9,000 acres. Some of the ways in which the farmers are using this is one of the things we do is microclimate prediction. That is, once you put this sensor in the farm, we don't only tell you what is the sensor value right now, we tell you what these values would be up to 5 days in advance. What you're seeing here is you should look at the red bar, What it is saying for soil moisture and soil temperature, even up to 5 days in advance, the error is less than 10%. And the way we built this model was we took weather station data from 50 weather stations across Washington state. We used that to train the model. And then this is like over the last 7 years, it was at every 15-minute intervals. And then what we do is whenever a farmer puts in a new sensor, we use a technique called transfer learning, using which we can start making very hyperlocal predictions of what's going to happen in the farm. That is, we talked a lot about variability in the farm. That is, even within a big farm, your rainfall changes from place to place. Your soil moisture varies from place to place within that farm. Using this with very low-cost sensors, you can start making those predictions of how these things vary in different parts of the farm. In the bottom left, you're seeing a testimonial by one of the farmers that we work with. This is a farmer who farms in 9,000 acres in eastern Washington. He was going to spray herbicide in his farm. The weather forecast said it's going to be 43 degrees in his farm. He would have gone in 43 degrees Fahrenheit. He would have gone and sprayed in his farm. It actually turned out to be 32 degrees, and we predicted it was 31 or something like that, where if he would have sprayed when it was freezing, the plants would have died. This is another use case. This is a farm in upstate New York. This is a 4-kilometer stretch. The farmer wanted to know how his cows are doing once they're out in pasture. We flew the drone, transmitted the data over the white spaces to an edge device, and within 30 minutes, we could start flagging things like from left to right, the grass is growing back well, there is a water puddle that needs to be fixed before the next planting season, the cows are pooping well, which is also important information for the farmer. This is deep learning on cow poop. We had an intern look at a lot of cow poop to train the model. This is where the cows are. This is a stray cow that needs to be herded in. All of this within 30 minutes of flying the drone. This is the farm close to Microsoft campus, the one I was saying where we do a lot of demos. We show the farmer these beautiful pictures overlaid with data. For example, in this case, the bottom left part of the farm, we were able to flag that it was moist, even though we did not have a sensor over there. This is a soil pH map. After the farmer had applied lime, we were able to flag that those dark parts in the farm are still acid. The farmer needs to reapply lime before planting the seeds. The question you would ask is, how accurate are these maps? Sorry, I don't have that slide. Yeah, there's another slide, but if you're interested in the research paper that we have on this, we have an evaluation of how accurate this is. We got the results over 3 different 5-acre plots, and then we said, we took 1,000 measurements each, and we said if we pick just 10 of these measurements, how accurately can you predict the remaining 990 points in the farm? And we saw that it's within reasonable accuracy, we're able to make those predictions. And in the paper, we compared that to state of the art, where we showed that this is 3 times more accurate than just using the Kregging's method of making these predictions of these variables throughout the farm. This is another use case where we have cameras in 3 different barns transmitting data over the white spaces to an edge device where you're seeing if the cows are moving well, a cow is sick, and so on, and flagging this information to the farmer. So this is something which I started this project in 2015. About 1.5 years back, I moved to the products in Microsoft, and we shipped a product, Azure FarmBeats. Now it's available on Azure Marketplace. You can go and install it. And here in this slide, what you can see is how we are taking it to market. Microsoft is not an agriculture company. The things you saw me talk about here are all enablers for you to do your research even more, to be even more productive in what you do. And so even over here, what we are doing is everything in yellow that you see on this slide is the way we are taking it to market. That's where we are working with partners. And this is for you all as well. That is, what we are building are things in green and blue. That is, you can get all the data in the cloud. We are providing the TV white spaces. We are providing the edge architecture. We are working with partners who build sensors. But once it gets to the cloud, we've integrated it with Jupyter Notebooks, using which you can start bringing in new AI. You can start writing your own AI algorithms on top of FarmBeats. So that said, this is what shipped, and in November, we announced it's in preview. So it's available right now. If you search for Azure FarmBeats, you'll be able to go and start using it. That said, we are continuing to push the boundary even further. That is, we have been able to solve some of the problems, but I wouldn't say that we've cracked this thing of making it affordable, especially for smallholder farmers worldwide. To solve that problem, we are continuing to push the boundaries. One of the things we are doing is we've come up with a way to measure soil moisture and soil EC using Wi-Fi signals. So the problem is the following. So these people right now use these probes to measure, say, soil moisture or electrical conductivity. These probes are expensive. A reasonable industrial grade soil moisture probe will cost a few $100s. And well, for most farmers, they wouldn't spend a few $100s to buy a probe to measure soil moisture because it's only telling you what's happening there, not what's happening 10 meters away. So to solve that problem, our insight was that many farmers, they have a smartphone, even if it is an inexpensive smartphone, an Android smartphone. If they have a smartphone, it has a Wi-Fi chipset in it. So the key insight was, if they have a Wi-Fi chipset, if we could measure the time of flight of a Wi-Fi signal, you can then use that to estimate soil moisture and soil EC. The physics behind it is that the time of flight of an electromagnetic signal depends on the permittivity of the material through which it is going through. So if the soil is moist, it will take longer to go that distance. If it is dry, it will go faster. It's the same way GPRs work, the ground penetrating radars work. The thing is, with Wi-Fi, ground penetrating radars, they operate in 1.2 gigahertz of the spectrum. You don't have that much bandwidth in Wi-Fi. So the question was, how do you build such kind of a system? How do you measure time in nanoseconds using off-the-shelf Wi-Fi chipsets? So that's what we built. We built a system called Strobe. This paper got the Best Paper Award in an ACM conference last year, where what we're doing is, instead of measuring the actual time of flight, our key insight was that most of these chipsets have multiple antennas. If they have multiple antennas, you can measure relative time of flight much more easily. And that's the thing we showed in the paper, and we compared it here with some of the state-of-the-art Decagon sensors, and we showed that it is close to the actual values that were measured with these industrial-grade sensors. So when the blog that Bill Gates had written on this, he titled it based on this research, he called it, "Can the Wi-Fi in your phone feed the world?" And we believe that's possible in the future. This was just the first paper. Of course, it's still in research, but we believe that future is possible. The other thing we built is just to push the boundaries even more, making it even more easy to use AI in agriculture, is we are building these kind of 3D simulation models for farms. The reason we did that is we get approached by a lot of drone companies who come and say, hey, you know what? We have the best AI algorithm to say, predict yield, to measure leaf area index. The question is, how do you even validate whether what they are saying is correct or not? That is, if you really had to measure and evaluate an algorithm to see whether they predict leaf area index accurately, you have to pluck every leaf, dry it out, and then measure the leaf area, which is not possible. Instead, what we did is we constructing these virtual farms. These are 3D farms where this is a physics-based simulator. You can change the weather, the wind, the sun. You can make it rain in this simulation as well. And then you can change the crop height, the crop spacing, the crop stress level. Once you do that, once you've created a farm of your choice, you can then go in this farm and you can fly a drone on top of it in this virtual farm. You can put this camera on a tractor as well. And once you do that, we then take this image, we push it through the rest of the drone pipeline of stitching, and it goes to the FarmBeats data hub in the cloud, where then you can start evaluating all the machine learning algorithms to see how well it performs. The interesting thing is, because this is in simulation, you know the features of every plant. You know the actual leaf area index of every leaf. So you can start making very accurate measurements using this. You can also use this to train the machine learning model as well. So at Microsoft, I talked about some of the work we are doing in research. There are others that we are doing as well on indoor farming, which I didn't get to talk about. We are building a lot of products in this space, but we are taking it a step further. This goes back to the discussion we had in the previous panel, which is about just building these digital techniques is not good enough. You need to educate the farmers on the benefits of these digital technologies. You need to skill them. You need to train them. So for that, on the right side, what we're doing is we are taking steps through our CSR initiatives, the corporate social responsibility initiatives, to take some of this work and partner with existing organizations to take this work to the growers. Through the Airband initiative, I talked about how we are working to provide broadband to the rural community. Through TechSpark, we've actually partnered with the FFA, the Future Farmers of America. So the FarmBeats system I talked about, we created these FarmBeats student kits. And last year, we actually held a competition where there were a few hundred FFA high schools. They applied for this competition. We picked 50 of them as winners, and to each 50 schools, we gave 2 of these FarmBeats student kits. And then we had a hackathon at Microsoft where we got these teachers on Microsoft campus, and we hacked on how would you get these kits as part of the high school curriculum. Our vision here is, how can you get students trained to use all these digital agriculture technologies? How do you get future farmers to start seeing the benefits of data? And by the way, the student kit I talked about, we actually are working with Cornell on the Cornell Initiative in Digital Agriculture, which Susan McCooch is leading. And we had a hackathon last week where we provided these FarmBeats student kits, and there were 8 of these teams which are actually building on top of these student kits that we had provided to Cornell. So going back, our vision here with all of this work is that we want to get agriculture to be cool again. We want a lot of farmers, a lot of next generation farmers who are going away from farming to see how technology can be used to come back to agriculture. So that's the vision, but also along that way, we want to use technology in different ways to help solve the problem of sustainability. So going back, so that's what FarmBeats is. FarmBeats is a way to allow you to get large amounts of data that you just couldn't get from the middle of the farm, and then bring in all the latest advances of artificial intelligence and machine learning to agriculture. So using this, we believe we can get to a future which is sustainable, as well as we're able to solve the problem of more food that the world needs. Thank you.
One clarifying question.
Is moisture content for what depth, and is it on mass basis or volume basis?
So you mean with Wi-Fi? Or yeah, with Wi-Fi we've gone up to, so depending on what frequency you use, if you use 2.4 gigahertz, we can go up to 30 centimeters. If you use the white space spectrum, we've done that as well. You could go up to 1 meter, and we're talking of volumetric.
Is it mass basis?
Yes, yes. So it is mass basis, and we've done this in limited trials, and EC as well. The other thing I didn't talk about was it's both mass and EC. And the interesting thing is when you're looking at, right now it's at a certain depth, and what we are telling you is the average moisture, average EC. If you use just one antenna, if you use multiple antennas, it's going to tell you at that depth, what is that value. So we can do both of them. I'll send you the paper. Would love your thoughts on it.